Hello. Now there's going to be people coming from next room, from next door. We'll have Juan Alonso to tell us about how the webcam can also be a musical instrument. Let's see what we learn from here. Hello. Hello, everybody. Thanks for being here at 4:30 at the very end, on the last stretch of this year's Route 8. This is usually a practical workshop because otherwise you are going to see me commenting code lines and it might sound weird, but if you want to follow this at the same time as I do the stuff, there is a repository in GitHub where you have all of the environment that you will have to have installed and the code base to be able to follow the examples. Okay, my name is Juan. I work in the company that used to be known as Tecnológica. And I've been dealing with programming all my life. And when I saw that in the call for papers, the organizers were looking for workshops about sort of more creative stuff, I thought this is my opportunity. I wanted to tell how to use programming for more playful stuff to get out of the machine code and do more fun things or us entertaining or with a different degree of creativity or a different touch. Because to learn while you play or either to learn in a more creative way or in a more playful way, I believe is perhaps not a more valid way to learn, but perhaps a more permanent way of learning. So the talk is divided in three parts. First of all, an introduction, which is what I'm telling you now. Then I'm going to talk about the parts of the ecosystem we're going to be using, and finally to develop a small musical instrument that's going to be controlled from the webcam. For the webcam part, the the image is not has not got the right proportions. I don't know if you're familiar with OpenCV, which are libraries created by Intel almost in 2000, in 1999, I think. And they wanted to do two things. First of all, they wanted to prove the power of their new processors, and finally, and afterwards, they wanted to provide programmers with some tools so that they didn't have to reinvent the wheel every time, and they focused on the graphic side. So these are libraries in C, C++, but they've ported for Python, Java. It works on Linux, Android. So for 18 years they've been evolving, and I don't remember when. I think it was about 5, 6 years ago it was done in open source. Therefore now everybody can see how they're done and contribute.
Em, Son unas librerías.
So these libraries allow you to do pretty much everything with images, from very simple things such as switching the contrast, having them in black and white or calculating the histogram, up to more complex things such as looking for lines or circles, or more complex things such as detecting faces, blocks, following moving objects, and eliminating the static background in video streams. So these are very powerful libraries that are quite complex to manage too. There's always been some sort of leap in difficulty, and one needed to work hard on this and devote a lot of effort to become a OpenCV master. In fact, if you check the manual, there are some functions and methods whose explanation is just a 5-author paper with 15 sheets of mathematical formulas. So before maybe they didn't understand how this worked, and after reading the paper they didn't understand it either, and you get a headache on top of that. So processing is a programming language and a development environment created at the MIT at the same time as OpenCV in around 2001. The idea was how they thought about the challenge of teaching programming to students in a visual way. Not visual to link parts or pieces, but visual because on the output wasn't just text, but that it would be very simple to create, change, and interact with graphics. So they wanted to do something more expressive rather than functional. They started using this as animation and prototyping for data visualization, and after 16 years, this environment is being used in production because FC is very stable. The underlying platform is Java, but the syntax for the users is a very simplified Java syntax. And it has certain libraries, and if at some point we need the ad hoc processing library, you can directly use a Java library. So the code is translated into Java, it's compiled and executed, and this is also multi-platform. The environment is available for Linux, Mac, and Windows. And with any of those three instances or environments, you may generate an executable file for the others. So the aim of this workshop is to use processing to link OpenCV and the audio libraries that the processing version 3 has to create a little music instrument. There's going to be some sort of terming to look at processing, OpenCV, and how to treat the audio libraries. The audio libraries for processing already existed for a while, and after version 3 they became a standard, and they're now in the core distribution. However, the ones introduced here are not the most powerful. There are others that do many more things, but for this example, and to rise our curiosity, this is good enough. So let's talk about how to join these parts, how to join these pieces. The processing programs okay, just a quick second. I should be able to show you some code. Okay, I know what's happening. So initially first, we're going to see the structure of a sketch or the processing program, then how to have access to the camera, and how that camera can be created with a couple of lines just to show the stream produced on the screen, to add OpenCV, to add the sound, and then to finish with a colorful part to allow us to manage our terming. So the sketch structure is very simple. There is a setup method executed just once when the program starts, and then there is a draw method that is executed continuously. I think that the processing tries to do it at 60 photograms per second, and if they can't, they're going to slow it down. But they don't skip any photogram, because in those they also carry out calculations. The function is called draw, but in that function or that method they do an update changing of all the parameters changing from one photogram to another, and then you depict it on the screen. This is basic structure, but you couldn't even skip the setup. And access to the camera is very simple. You just load the library, and declare a video type object. Next, if you say that the video stream is going to measure 640 to 480, and you begin the camera. Once you start the camera, because naturally you only start the camera once. So this part, video and video start, will be in the setup. And once we start the camera in the draw, we collect all the photograms and we paint it on the top left side of the screen, a 0, 0 position. Here we access the camera of our laptop and we are painting the string of images that it produces. And next we're going to get to the examples. After this we use OpenCV. We have the video stream from our camera and we're going to try to treat that video stream to extract some information that we'll give to our music instrument. It's one that our musical instrument will use as a basis to create different sounds. Here we're not going to use the OpenCV Java libraries. And this is only half true. We're going to use a wrapper created by a programmer called Greg Borenstein. He's uploaded it to GitHub. And this locks up the CV methods to really ease the way of using it. So just like in the case of the camera, we declare an OpenCV object. We created in the setup method with the same dimensions as the camera stream. And next we load the images provided by the webcam where it says magic. We add all the OpenCV functions that are executed one after another. And the author here created destructive actions. So I applied against a contrast with an object, and then the line detection is done on the image on which I apply the contrast, not on the original image. This is very comfortable for simple workflows, and if we need a more complex workflow, we need to dig a bit more in OpenCV to get a copy on the one hand, manage the object on the other, and then link them. You'll see this is very simple. And to sum up, we get a video image, we add it to OpenCV, OpenCV works its magic, and next we paint that on the screen. And let's begin with the first example. Otherwise it will be a bit boring. And this is when the screens are going to dance a little bit, so please be patient. And I never find my cursor, so here it is. So this is the phase of the processing development environment. It's not wonderful, but it's colored by syntax and it's pretty comfortable. There are ports for Sublime that allow you to use more useful or complex macros, but basically this is what we've seen. I import the CV and video libraries. I declare an OpenCV object and another one for video type. I say that my screen measures 960 by 360. I create the CV object, the video object, and here I saw the loop of getting the photogram. If it exists, I paint it on the screen, I put it on OpenCV, and after treating it, I paint it on the screen again. Here, since I'm not doing absolutely anything with the code, I just get on the left the image read by the webcam, and on the right the OpenCV image. Since initially OpenCV was geared towards detection, by default it works in gray colors, even though you may have access to different color channels. This is cool, but it's a bit boring. So let's have a look at some of the functions of OpenCV. For example, a quick one is that we can actually make the image negative. Here we are. And this is just a line. We can even calculate and change the brightness of the image. Well, here we're changing the brightness. We can even make that brightness depend on the mouse position. Here we have the map function, and we say, okay, get the mouse copy. It may take a certain width, and we map it with certain dimensions. This is what the processing authors refer to when they talk about obtaining something in a visual and quick way, without having the need of learning the programming basics. To me, this is a definition I've always liked, and they say that processing is the programming languages that converts engineers in artists and artists in engineers. And we may apply some other useful functions here, quite useful, such as the threshold one. In this case, all the grayscale values will be painted as pure white, and all the ones below are going to be painted as pure black. Okay, and just like in the former case, we can make that threshold depend on the mouse position. So here, just like before, the mouse position may vary from 0 to the screen width, and we want to map that from 0 to 255. So now, the more to the right we move the mouse, the higher is the threshold. There will be less pixels that get painted in white, because the threshold says that from the value to the right everything will be white, from the value to the left everything will be black. Since the value is closer to 55, everything is black, or pretty much, and this could be useful to detect the brightest points of the image. For example, here we can see the focus and the light reflection in my hand. If we do it otherwise, this will be useful to detect the darkest points of the image. And here, there's a very interesting method in range to define a range value. Everything here within that value range is painted white, the rest is painted black. And let's see why this is interesting. Okay, so let's start making some noise. Okay, let's see how processing manages the sound. This is quite funny initially, but in fact, many of the system generation programs per programming use a similar method. So basically, apart from losing the mouth, I import the library and I create an oscillating object, which is a type of wave that I want to reproduce. In this example, we're going to treat a pure waveform that may be combined to have more complex waveforms, or we could use pre-recorded samples. But the only thing I'm saying here is that I want a triangle oscillator and I begin to reproduce it. The frequency of that oscillator will depend on the vertical mouse position, and the volume will depend on the horizontal position. And I hope you won't become deaf now. And I get the wrong screen for a change. Okay. So here the vertical position controls frequency, and the horizontal one controls volume. So this is quite cool, but initially it's a bit boring. So let's begin to do things with it. Instead of having a constant wave, we're going to start shooting the wave and change the frequency. We'll change the tone every now and then. So every 1500 milliseconds, you're gonna shoot a wave with a random frequency. This is not bad, but this is not exactly what should be happening. So why is this happening? Right now we should get some horrible sounds. Because the next thing I was going to explain was going to use the envelope, which controls the wave volume. Quite interesting, isn't it? Okay, here it is. What was happening there was that the oscillator was controlled by two pieces of code at the same time. So little by little we create some weird sounds, and every second and a half we add a new sinusoidal wave to the current sound. And the next thing is the envelope, which is the volume we give to the wave. So here we're gonna do this, and the wave is gonna start at billion zero. It's gonna begin its maximum volume at 5.5 zeros. It's gonna keep it for 0.2 seconds, and then it's gonna go down at 0.5 seconds, which is the beep we heard earlier. Okay, so let's do it a bit more quickly. Okay, so this is taking shape, although it's out of tune. And next we'll assign these notes to the notes of a piano keyboard. And we have this mathematical function. What we're doing now is just to run some random frequency through it. And there, the one assigned by the random might not fall between two notes. This is why it's out of tune. If we use this function, we're actually converting the frequency to frequencies that fall exactly within the piano notes. And this basically chooses a random value of this array that corresponds to the black notes of the piano. The number is converted into a frequency, which is just a mathematical operation, pretty simple. And here we know which frequency is used. It's equally random, but at least it's tuned, well tuned. Okay. And the next step we're going to take here is to add color. If you may remember, OpenCV gets things with different grays, but we can have access to that in different colors. And here we have the traditional one. The first one will be R, then G, then B. And the row below is HSV, which is a bit less intuitive, but to do things with colors is it works very well. Instead of having a channel for red, another one for blue, another one for green, it has a channel for color. It with the red, which will be the black color, and then it turns until it gets to red or purple, that is 255, and this is easier shown in this chart. This is how design programs in colors work. Here we have a continuous gradient of colors. In the case of HSV, it will go from 0 to 255, and we're going to see that now on the lower left corner of the screen. The other two values, the other two screens, correspond to saturation and brightness. For this example, though, we do not need them. So which are the advantages of using HSV? If we execute this again, if I can get control of the mouse, and if we execute the program again, if you look at the RGB, you may notice that I don't have an easy way of distinguishing that this notebook is blue, because when you say, okay, it may have a little red, it may have some green, and the blue channel might be brighter. But if we go to the color channel, down to the left, we see that we could choose a more or less defined color range, which is what we're going to do in the next stage. And this is going to be quite funny with the screen at the back. And with this, we're going to set our term in. And I have just a few minutes left. But the structure is the usual one. I create a screen of 960 by 360, my PenCV object, my camera object. I start the camera, and here I'm going to use a sound oscillator. I read whatever comes from the screen, I paint it per screen, I transfer it to OpenCV and I paint it there. Like the beginning, on the left I have whatever I get from the webcam, and on the right the stuff that I have treated. So I'm interested in detecting this shade of blue. So I'm going to tell OpenCV to use the HSV color space in case it's HSV or HSB, but in the functions it's HSV, but it doesn't matter. So we say, okay, transfer the image to HSB and keep the H channel. Then I'm gonna put it out of focus to avoid noise, or dissimulate it to mask the noise. So on the left we have the original image, the one on the right is treated with the blur and the HSB channel. And now I want to isolate the blue. If you may remember, right at the beginning, we said that there would be a function that would allow us to get a range of values and set it to 1, and the rest will be left at 0. So that's what I'm going to do now with the screen on the right. You're going to try to isolate the blue color. So these shades of blue correspond to between 95 and 113. If everything goes okay, now in white, I should get this. Okay, it's detecting a few more things, and in fact, let's see how I'm doing. Oh, gosh. So if you notice, from the color channel we have isolated the channel corresponding to the shade of blue. Let's see what we can do with this. OpenCV gives us the possibility of finding the polygon that contains this environment, this contour. So once it has a binary image, after we apply the scale of gray and some blur, when we apply the in range, and when we have the equivalent range of colors that is equivalent to this blue, we get a binary image. Only blue, only black, or only white. We can apply some geometric function, such as erode, that takes out noise. And then we have the OpenCV part. And it's hard to say, but there's a lot of trial and error here. In the handbook, they say that you should keep trying until you find the configuration that better fits the lighting configuration, the type of image you're treating, and so on. And what we're going to do here with this function is to generate some polygons. I'm gonna say that I don't want any holes in them, and I wanted to sort them from small to larger. If I take the first one, it should be the smaller one. So if it finds any contour, I'm gonna get the 0, the largest one, and I'm gonna ask it to paint it for me. Okay. And here you may see how it's painting on the image on the left. It's painting the polygon. So from the original image of the webcam, with a few simple transformations, we're getting the polygon with a particular color. And now we're going to find the center of that polygon, because with this function I can do different things. First, I'm going to get it to choose a rectangle, including that polygon, and I want to include the center and paint an ellipse that will have a circle in that center. And now that circle is the one that I'm going to use and just like I was using the mouse to vary the frequency of the sound, I'm going to use that circle to generate sound and vary the frequency. And it's like as simple as saying, okay, in the circle position I've got it calculated here, and I may say, well, give more volume to the waveform, the frequency I want goes from 0 to the width. The circle will be between 0 and the width, so I want the frequency to be between 220 and 280. So I give the frequency to the oscillator. Okay, so here we are using the center of the folder as a reference point to generate noise. And seeing that I just have a few seconds, as I promised when I described the workshop, this should be well tuned, and that's what we're going to do next. And I can actually activate this whenever it takes faces and things like that.
Hacer es
So what we're going to do is that right now the frequency is going from 220 to 880. Well, I wanted to go from 1 to 8 now. Why? Because it's the number of elements. Okay, 1 to 7, because this is the number of elements I have in this array, and they match the black notes of the piano, because it's the pentatonic scale that sounds a bit like false Chinese music, but it sounds in tune. So what we do is that the circle affects not the frequency but the index within that array. And as in the previous case, what I do is I apply this transformation that shifts from a piano note to frequency. Okay, that's what I wanted to tell you in this workshop. There are lots of technologies. There are lots of interesting things. There's a creative side that allows you to do very fancy stuff with relatively very little work. So if you go to the description of this workshop, or you write down this address, you have here all the code, all the instructions to install the development environment, how to install the libraries, and you can have this working in 10-15 minutes. It's not a struggle at all. So that's all. Thank you very much to organizers, and thanks for showing up on a Saturday afternoon. And for anything you need, you can get in touch, and you can get in touch with me either with my email or my Twitter account. Any questions? Hello. I also like music a lot, and I wanted to ask you, can you export to MIDI all with these libraries? Not with these ones, but I think with ones that processing includes. It can read MIDI. I'm not sure because I've used it to read MIDI, but not to generate. But you can use Java MIDI, but at least record the sound in an audio stream. Yes, because you can do streams that you can redirect to different output points. But as I said at the beginning, since this is based on Java, so if the library doesn't have that possibility as such from Java.MIDI, you can generate the MIDI files. Okay, thank you. Any other questions? Okay, then let's go for coffee. Or translated into a Java